Welcome in this lecture. Today we will discuss about voltage regulation in transformers. We know that when a transformer is loaded, that is load is connected on the secondary side of the transformer, the current increases, and because of increase in current, there is voltage drop in impedance of the primary and secondary windings of the transformer, and due to this voltage drop, the terminal voltage, secondary terminal voltage of the transformer decreases, and this decrease will depend upon the amount of load on the transformer or load current. That is, this drop increases with the load or increases with the increase in load current. So this drop in voltage when transformer is loaded is known as voltage regulation. Drop in voltage in secondary winding or secondary terminal with respect to the secondary load voltage is known as voltage regulation. So we will explain this voltage regulation by taking example of the circuit of the transformer. It means we will draw the schematic of a transformer and explain what is secondary terminal, what is no load voltage of secondary, what is load voltage of secondary, and then we will define the voltage regulation. Suppose our transformer schematic is, this is our core, and on the core we know that we have our primary winding. Suppose this is our primary winding, and in primary winding it has some resistance and it has some inductance, suppose R1 and X1, and here we apply AC voltage, that is V1. We apply here AC voltage, that is V1. This voltage is V1. Now this current is I1, and a flux is set up in this core, and this flux is shown, and the direction of this flux will be like this. So this is, you can say, flux phi. This is known as mutual flux phi. And now we have our secondary winding here. So this is our secondary winding. This is our secondary winding, and secondary also has resistance and reactance. This is R2, this is X2, and this is the secondary terminal of the transformer. When we apply here, a current will start flowing in this winding, and this alternating current, since alternating current means changing current, it is changing with respect to time. So there will be a changing flux in this core, and flux will follow the minimum reluctance path. That's why all the flux will flow through this core only. Core, you know, it is made of magnetic material, iron. Now this flux, since it is alternating, means it is changing in this winding, that is secondary winding. So there will be an induced voltage here. This is known as E2, and here will also be a induced voltage, that is known as E1. And now this is available at the load terminals. You can say this is load terminals. Here we can connect load. When we have not connected any load here, this voltage E2 whole will appear here, and when we connect a load, then a current will start flowing in this, and because of that current there will be a voltage drop in this. And similarly, when this current starts flowing, an additional current starts flowing here also. So it means here will be voltage drop and here will also be a voltage drop. Hence we will get a voltage here known as V2, and this is known as load voltage. V2 is known as load voltage and E2 is known as no load voltage. So this V2 will be less than E2 sometimes, and it will be more than E2 next times. So we will explain when V2 will be less than E2 and when V2 will be more than E2. So we will explain by taking the phasor diagram of this. Now suppose what is we have said E2 is this E2, it is secondary terminal voltage on no load, and V2 it is secondary terminal voltage on load. Now we have said that there is generally loads are of lagging power factor nature, and that's why in the case of lagging power factor nature of the load, this voltage will be less than E2 and there will be a drop in this voltage, and voltage regulation, which is defined as voltage regulation, we define voltage regulation. What is voltage regulation? Voltage regulation is defined as drop in voltage across secondary terminals when load is connected from no load voltage to full load voltage with respect to the full load voltage. That means voltage regulation is defined as drop in voltage. So drop in voltage, it is E2 minus V2 upon V2 with respect to secondary load voltage. V2 is secondary load voltage, E2 is secondary no load voltage. So this is per unit voltage regulation. Per unit voltage regulation. Voltage regulation in per unit. We can say percentage voltage regulation. Percentage voltage regulation, it is what we do, we will simply multiply by 100. So this is E2 minus V2 upon V2 into 100. So this is our voltage regulation. Now this voltage regulation, sometimes it will be positive and sometimes it will be negative. So how we can explain? We will explain this by taking the case of a lagging power factor load, and we will see that in case of lagging power factor load, voltage regulation will be positive, and when we will take a leading power factor load, then we will see that the voltage regulation will be negative, and this thing will be explained with the help of phasor diagram. So we will, before coming to this voltage regulation at different nature of the power factor, different nature of the load of the power factor, we will see how it varies with load current or with load. So let us see variation of voltage regulation with load. Right. So this is variation of voltage regulation with load. Suppose we are saying that this is our voltage axis, voltage, and this is our load current. When load increases, load current increases. Suppose this is the value of our no load, this is the value of our no load voltage. No load voltage on voltage axis, suppose its value is like this. Now suppose we are considering a lagging power factor load. When we consider a lagging power factor load and go on increasing the load, load current will increase, and when load current will increase, the variation of the terminal voltage, variation of the secondary terminal voltage will be like this. It means this is with leading, it is with lagging power factor load, with lagging power factor load. This is with lagging power factor load. And in case with lagging power factor load, we can say E2 is greater than V2. E2 is greater than V2. This is no load voltage. No load voltage means E2, right? And as we are considering leading power factor load, capacitive load, so with increase in load, this load secondary load voltage, secondary terminal voltage on load decreases. So we get a curve like this, variation of secondary load voltage with load current. And when E2 is greater than V2, we will get positive voltage regulation. We will get positive voltage regulation. And same thing, suppose we are considering now a leading power factor load. When we will consider a leading power factor load, what will happen? When we will go on increasing the load and hence the load current, the variation in secondary terminal voltage will be like this. Variation in secondary terminal voltage will be like this, and this is for with, we can say, leading power factor load. Leading power factor load means V2 is greater than E2. V2 is greater than E2. So we know that our formula of voltage regulation is percentage voltage regulation. It is E2 minus V2 upon V2 into 100. So this is the expression of voltage regulation. When V2 is greater than E2, what does it mean? This becomes negative. Hence, for this we get negative voltage regulation. For this we will get negative voltage regulation. Okay. So this is explanation how with variation of load and load current and variation of nature of the load, the voltage regulation varies. Sometimes it is positive, sometimes it is negative. We have seen that with the lagging power factor load, voltage regulation is positive, and with leading power factor load, voltage regulation is negative. And these questions may be asked in MCQ. This is important with respect to MCQ questions. Now we will consider the first case, that is lagging power factor load. We will consider lagging power factor load, and we will prove that how with the lagging power factor load our E2 will be greater than V2 and our voltage regulation will be positive. Similarly, second case we will take with leading power factor load, and we will show that V2 is greater than E2 here and voltage regulation becomes negative. So we will considering the, first of all we will consider the voltage regulation with lagging power factor load. So we will consider a lagging power factor load voltage regulation with lagging power factor load. Now we know that for lagging power factor load, we will draw the phasor diagram first, and before drawing the phasor diagram, we know that from equivalent circuit of the transformer, the voltage equation of a transformer, voltage equation of a transformer, from equivalent circuit we have derived this equation, that is E2 will be equal to V2 plus I2 R2E plus J I2 X2E. So this voltage equation we have derived from our equivalent circuit. E2 is our no load secondary terminal voltage, V2 is our secondary terminal voltage on load, and I2 is secondary current, secondary load current, and R2E is equivalent resistance of transformer, and X2 is equivalent reactance of transformer. So we will now draw with the help of this equation. With the help of this equation, we will draw the phasor diagram. And to draw the phasor diagram, take V2 as reference. Take V2 as reference. When we take V2 as reference, our phasor diagram we can draw very easily. Suppose we are taking lagging power factor load, and suppose the power factor angle is phi 2. Power factor angle is phi 2. What does it means? It means that our load current will be lagging the load voltage by an angle phi 2. This is meaning of phase angle phi 2, power factor angle phi 2. Power factor angle phi 2, and taking V2 as a reference, we can draw now the phasor diagram. Suppose we are taking V2 like this. This is our V2. Now suppose we have drawn V2. From V2 we know that this is our V2 load voltage of secondary load voltage V2. Now I2 will be at an angle of phi 2. Suppose this is I2. This angle is our phi 2. Now we have drawn I2 at an angle phi 2 because power factor angle is phi 2 and it is lagging power factor. So it will be lagging with V2 by an angle phi 2, and lagging, you know that we have discussed in phasor diagram. We show I2 below the reference axis, and reference axis we are considering V2. If it was leading, we will show this I2 above this V2 reference, above this V2 reference. So this concept you know from phasor diagram. Now we have to complete this equation. In drawing phasor diagram, you have to simply complete this equation, and for completing this equation, E2 will be V2 plus I2R2. V2 plus I2R2 means we have to add a phasor I2R2 in V2. So where will be phasor I2R2? I2R2 will be in phase with our I2 from the end of the V2. From the end of the V2, we will draw a phasor. This is a phasor which is parallel to I2, and this is known as I2R2E. So this is a phasor parallel to this. Now we have to add this one Ji2x2E in this phasor to get this phasor equation. So what we will do? Ji2x2E, we will draw a phasor at 90 degree to this direction anti-clockwise. 90 degree anti-clockwise. So this will be direction of Ji2x2E. This is the direction of Ji2. This angle is 90 degree. This angle is 90 degree. This angle is 90 degree. At 90 degree, now we will get, we have added in V2, we have added I2R2, and we have also added Ji2x2E. So I2R2E, Ji2x2E, and sum of all these is our E2. So we will get our E2 as, this is our E2. This is our E2, the secondary terminal voltage on no load. So this was secondary terminal voltage on load, and we have added the drops in impedances of the transformer. We have got the secondary terminal voltage on no load. So this we have got, and from the phasor diagram we can clearly see that our E2 is greater than V2. It means positive voltage regulation. It means positive voltage regulation, because we know that our voltage regulation is E2 minus V2 upon V2 into 100. So it will be, since this is, so this will be, you can say it is positive, since E2 is greater than V2. So from the phasor diagram it is obvious. Now we have to write the voltage regulation in terms of parameters of the equivalent circuit of the transformer, and parameters of equivalent circuit are R2E, X2E, I2 and V2, etc. So we will write this with the help of, this phasor diagram itself. So suppose this point is O and this point is A, and this point suppose it is B, and suppose we are extending this, we are extending this, we are extending this, we are extending this, and we are extending this as parallel, and we are drawing a perpendicular from here, perpendicular from here, and we are naming these points now. Suppose this point is F, this point is D, and this point is C, and now suppose this angle is alpha, this angle is alpha. Now we want to find out OC, and to find out OC in terms of V2, I2 R2E, I2 JX2E. How we will find out? For we know that practically alpha is very small, alpha is very small, alpha is very small. When alpha becomes very small, this angle becomes very small. What does it means? It means that suppose we extend this, and suppose this point is D and this point is E, then for alpha very small, we can very easily see that this alpha is very small. So it means OC will be approximately equal to OD. It will be very approximately equal to OE will be equal to OD. That is, our E2 will be OC is equal to OD. How we can calculate our OD? OD from the phasor diagram, we can see that OD will be OA plus AF plus FD. Now OA we know, and OD is our E2. OD is our E2. OA is, what is OA? What is OA? OA is our V2. So we are taking V2, and what will be AF? AF, this one. This is a right angle triangle, and this angle it will be phi 2. This angle will be phi 2. So in this right angle triangle, FAB, this is base, this is perpendicular, this is hypotenuse. So we can write AF is equal to I2 R2E cos phi 2. So AF will be I2 R2E cos phi 2, and plus FD. FD is from this figure we can say FD is equal to BE, and BE we can write from this right angle triangle, and from this right angle triangle we can very easily see that this angle is also phi 2. This angle is phi 2, and because this angle is phi 2, so angle between these two lines is phi 2. Hence, angle between lines perpendicular to these lines will also be phi 2. Based upon that concept, we have written this angle as phi 2. Now, we can see that FD will be equal to BE, and BE will be nothing but this is your I2 X2E. So, I2 X2E sine of phi 2, sine of phi 2, because this line is, this length we have shown E, this is nothing but I2 X2E. So that's why this is sine of this angle will be this upon this, hence this angle, this side BE or FD will be I2 X2E sine phi 2. So we have got this equation of E2, that is no load secondary terminal voltage. Hence, we can say that voltage regulation, percentage voltage regulation it will be E2 minus V2. So E2 minus V2, V2 will be cancelled out, and we can say I2 R2E cos phi 2 plus I2 X2E sin phi 2 upon V2 into 100. So this relation we have obtained, and this is our positive. This is positive. So expression of voltage regulation in terms of parameters of the equivalent circuit of transformer, parameters of equivalent circuit R2E, X2E. R2E, X2E are the equivalent resistance of transformer. So we have explained this with the help of phasor diagram and shown that it will be positive because E2 is greater than V2. Now we will consider our transformer with the leading power factor load, and we will show that with the help of leading power factor load, voltage regulation will be negative. Why voltage regulation will be negative? Because in case of leading power factor load, E2 will be less than V2 or V2 will be greater than E2, and that's why voltage regulation becomes negative. Now consider leading power factor load. Now consider leading power factor load. So we will consider now voltage regulation for leading power factor load. Leading power factor load. Now for leading power factor load, we will use the same concept, that is our same voltage equation from equivalent circuit. E2 will be V2 plus I2 R2E plus J I2 X2E. We will use the same voltage equation discussed earlier, and we have shown how with this voltage equation we can draw complete phasor diagram of the transformer. Now we are considering the leading power factor load. So as in previous case, we will again take V2 as reference. V2, suppose V2 is here. So this is our V2. We are taking V2 as reference, and we are saying now ki it is leading power factor. Lagging power factor we have drawn below this current, we have drawn below this reference voltage. When it is leading power factor, then the current will be above this reference line, and suppose our current is here. Our current is here. Current is here. This is our load current I2 at an angle of phi 2. This is load current I2 at an angle phi 2. Now we can complete this. We have to add I2 R2E in V2. Where will be I2 R2E phasor? How we can draw? From the end of this V2, we will draw I2 R2E phasor, and I2 R2E phasor will be in parallel with I2. So now we will draw a phasor which is parallel to this phasor, and parallel to this phasor it will be, suppose this is your I2, we should not write this I2 R2E, suppose I2 R2E. This is I2 R2E. Now this I2 R2E is in parallel with I2. So we have added I2 R2E in our V2. Now we have to add I2E X2E. I2 this is not E. So I2 X2E. I2 X2E phasor, that is J I2 X2E. J I2 X2E will be anti-clockwise, 90-degree anti-clockwise from this direction. So from this direction, a phasor which is 90-degree. So 90-degree anti-clockwise. This is direction of, we can say, the phasor I2 R2E. A phasor at 90-degree will be like this, and its magnitude will also be something higher than I2 R2E. A phasor which is at 90-degree will be like this. So this angle is 90-degree. Now this is your I2 X2E, J I2 X2E at 90 degree. Now we have added J I2 X2E in V2 also. So hence our E2 will be this one. Our E2 will be this phasor. This is our E2. This is our E2. This is our E2. Now we can very easily see that for leading power factor E2 is less than V2. Once from phasor diagram, it is obvious that E2 is less than V2. Hence our voltage regulation will be negative. Voltage regulation will be negative. Now we want to find out parameters of this voltage regulation in terms of parameters of this equivalent circuit, and parameters of this equivalent circuit are R2E, I2E, X2E, R2E, X2E and I2 and V2. So we will derive the expression of voltage regulation in terms of its parameters. To derive this equation, we will use this phasor diagram itself, and from phasor diagram we will write the equation of E2, and suppose we are drawing a line which is perpendicular to this line. Let us name these points. Suppose this is O and this is A. This point we are saying this is A. Now extend this also like this and draw a perpendicular from here. So we can see that this angle will be phi 2. This angle will be phi 2. This angle will be phi 2 because this line is extended horizontally and this line is parallel to this line. So that's why this angle will be also phi 2 because this angle is phi 2. So this angle will be phi 2. Now suppose we extend this point, and suppose we are saying that this point is B. We extend this point B parallel to OA. When we extend this line parallel to OA, suppose it cuts at this point, and this point suppose it is D. Suppose this point is D, and we are saying suppose this point is C. Now we can see that what will be this angle? What can be this angle? This angle. We can see that since this is phi 2, hence it is this angle is also phi 2, and this angle is between the lines perpendicular to this line and perpendicular to this line. This angle, this phi 2 is the angle between AB and we can say this line. So the angle between a lines perpendicular to this line and perpendicular to this line, that is this angle. This line is perpendicular to this one and this line is perpendicular to this one. Hence this angle will be also phi 2. This angle will be also phi 2. This angle will be phi 2. Now we can suppose we are saying that this is E. Now we can write the E2, our E2, and suppose in like previous case we are saying that suppose this angle is alpha, angle between E2 and V2. Suppose this is alpha, and as in previous case we are practically it is found that alpha is very small. Alpha is very small, and that leads to alpha जब बहुत small होगा तो this means what will be meaning of alpha? Very small. Alpha very small means this OC will be coming towards this OE. It means OC will be approximately equal to OE, and this will be equal to our E2. This will be equal to our E2. E2 will be equal to OC and it will be approximately equal to OE since alpha is very small. Now we can write E2 as E2. we can write E2 as, what will be E2 from this diagram? We can see that E2 means OE. OE means, suppose we are saying that OE will be equal to OA plus EA. We can write our we can write OA and suppose OE, we are writing OA plus, suppose this from this to this point, suppose we are taking as AF. So we can write OE as OA plus AF. We have added in OA we have added AF, and we want to find out OE. So in OA we have added AF and we want to find out OE. It means we have to minus subtract this EF. So this will be EF, right? So this will be OE. OE means this value we are saying OA plus AF minus EF. So now it is clear कि value of E2 will be OA plus AF minus EF. Now we can write these values. EF, what is OA? It is V2. And AF, what is AF? This is AF. Means we can use this right angle triangle BAF. In right angle triangle BAF we want to find AF. What will be AF? This is a base of this triangle, this is perpendicular of this triangle. So base upon hypotenuse, it will be cos of phi 2. It means AF will be I2 R2E cos phi 2. And what will be EF? EF means from here to here, and we can see that EF from this diagram, we can see that EF will be equal to DB or BD. DB or BD. EF will be equal to DB or BD. And from this right angle triangle DCB, we can find out BD. What will be BD? We will use this right angle triangle DCB. This angle DCB is equal to also phi 2. So we can use this right angle triangle. This is right angle triangle. By this right angle triangle, we can write what will be value of BD. BD will be I2 x2e sine of phi. Simply we will use this right angle triangle and we will get BD will be, and BD will be equal to EF minus I2 x2e sine of phi 2. So this we have got the equation of E2. That is the equation of secondary no load voltage. The equation of secondary terminal voltage on no load. We have got this equation in terms of parameters of the equivalent circuit of transformer. Now we can write voltage regulation. Voltage regulation, we know it is E2 minus V2 upon V2 into 100, and when we simplify, V2 will be cancelled out and it will be I2 R2E cos phi 2 minus I2 x2E sin phi 2 upon V2 into 100. And we know that in a transformer x2E is much more than R2E, hence this numerator will be negative and this voltage regulation will be negative. So this we have shown from the phasor diagram and simple mathematics that our equivalent circuit using equivalent circuit and phasor diagram, we have shown that our voltage regulation will be negative when transformer is supplying a leading power factor load, and voltage regulation will be positive when transformer is supplying a lagging power factor load. So it means the general equation of voltage regulation, we can write general equation of voltage regulation, percentage voltage regulation as I2 R2E cos phi 2 plus minus I2 X2E sin phi 2 upon V2 into 100. So this is general equation of voltage regulation, general equation of voltage regulation, right? And when we will take positive sign, we will take positive sign for lagging power factor load, and we will take negative sign with leading power factor load. So this is general equation of voltage regulation. So we have discussed in this lecture voltage regulation of transformers, and we know that voltage regulation of transformer is the relative drop in voltage of the secondary terminal voltage from no load to full load with respect to full load voltage, that is E2 minus V2 upon V2 into 100. It is percentage voltage regulation, and E2 minus V2 upon V2 is per unit voltage regulation. And we have seen that voltage regulation is positive for lagging power factor load and it is negative for leading power factor load. Thank you.